This is EE698I, Mixed Signal IC Design, and this is lecture number 7. The last couple of classes, we were discussing about how to measure the signal to quantization noise ratio of an ADC. And what we finally decided was the following. So we take the ADC and give a sinusoid at a frequency Fin, such that when the ADC samples the signal at a rate Fs, the discrete time sinusoid is of the form cos 2 pi m by n times n, right, where m and n are coprime, right? And this also means that we need to choose the ratio of the input to the sampling frequency to be this m by n. Okay, and what we do, we take n samples of this and compute the power spectral density at the output of the ADC. So let's say the output of the ADC is some signal V. So we compute the power spectral density as 1 by n times mod V of k squared, where V of k is the n point discrete Fourier transform, or the DFT of the signal. So this essentially computes the spectrum at these frequencies k 2 pi by n, where k takes values from 0 to n minus 1, right? So if I plot the power spectral density, say it's a two-sided power spectral density. So this is the axis k. I'll have values from 0, 1 till n minus 1, right? So this is nothing but 1 by n mod V of k squared. And of course, we take averages of this. Okay. So what we'll have, the input is on the mth bin, right? So we'll have an impulse at, say, the mth bin. And of course, I'll also have the negative frequency, right? So it will ideally be at minus m. But since I'm showing values of k from 0 to n minus 1, the negative frequency bin will be n minus m. Right, so this is similar to, a frequency minus omega naught, same as 2 pi minus omega, right? And all the other bins in between will be filled with noise, right? And in practice, as we discussed, we only show the one-sided power spectral density. That is, we show k from 0 to, say, n by 2. Right? And we know that a frequency bin k, for a frequency bin k, the corresponding negative frequency will be at the bin n minus k, right? So what we do, we take these bins, the negative frequency bins, and sum up the power in the both positive and the negative frequency bins and show only one side. Okay. So except these bins 0 and n minus 2, all the other bins in between. Okay, so let's say this exactly is my n by 2. Okay, so except 0 and n by 2, all the other bins in between will have a corresponding negative frequency component. Okay, so except these two bins, the strength of all the other bins will double, right? So we'll have something like this. Okay, so this is the one-sided power spectral density. Okay, and in MATLAB, this can be computed using this command called pwedge. Okay, and as it turns out, because of the way MATLAB does this computation, we also need to add a scaling factor of 2 pi. And if you do that, this exactly gives us for us, right? And we also saw that the total power in the signal is nothing but summation k equal to 0 to n minus 1. I also have a scaling factor of 1 by n. So let me push this up. 1 by n times SV of k, right? And if you want to find the frequency at certain frequency bins, I will just do 1 by n times SV of those frequency bins, right? Summation over those frequency bins alone. Right? And these scaling factors, this 2 pi, 1 by n, and so on, they do not make a lot. They do not make any difference if we are looking at the ratios of power, like we are doing in this case, right? We are trying to compute the ratio of the signal power to the quantization noise power. So even if you miss the scaling factors, the ratio does not change. Okay, but you should be careful when you're trying to compute the absolute power of the signal. Okay, in that case, you need to include the scaling factors properly. Fine. So let's say I take an ADC and I feed a signal such that after sampling, the discrete time signal is say cos 2 pi times 201 by 8192 times here. Okay, and say I take an 8192 point DFT and find the power spectral density. So let's see what we get. So this is the one-sided power spectral density. So I have this is the signal. Let me write it again. It is cos 2 pi times 201 by 8192 times n. Okay, so I'm taking a 8192 point DFT, and I'm showing only one-sided power spectral density. So I have bins from k equal to 0 to the last bin is 4096. Okay, and in the y-axis, what I'm plotting is the power spectral density divided by n. Okay, so please remember that if we take the power spectral density, right, and scale it by n, this directly gives me the power in that particular bin, right? So the value of each bin directly gives the power of that corresponding frequency bin. Okay, and I'm plotting this in log scale in dB, because in linear scale you might not be able to show such large, range of values, right? So first thing, notice that the signal has a power of around minus 3 dB. Right? That's expected because this is by signal U of n. Right? The amplitude of the sinusoid is 1, so the power is minus 3 dB. Next, notice that the quantization noise spectrum is almost flat, right? So and that's the assumption we had also made, that the power spectral density of the quantization noise is flat. Okay, and from this you can calculate the signal to quantization noise ratio, and you can find it to be around 62 dB. Okay, and this corresponds to an effective number of bits of roughly 10 bits. Okay, so till this point we have considered that if the input to the ADC is U, the ADC output is the input plus the quantization noise, right? So we assume that the ADC is linear, that is, it gives you the input and adds a quantization noise. That's how we have modeled it, right? But in practice, when we start implementing this using circuits, you'll find that the ADC will be highly nonlinear, the final implementation. So the output will have a form like this. So the output will be alpha 1 times U, say alpha plus alpha 2 times U squared, alpha 3 U cubed, plus say alpha 4 U power 4, plus all higher harmonics. And then along with that, you'll have the quantization noise. Okay. So, but let's say you implement the ADC in a fully differential fashion. These even harmonics will not be of concern, so they will go to 0. So we'll end up only with odd harmonics. So if you feed a sinusoid to such a nonlinear ADC, right? So let's say we give the same signal cos 2 pi times m by n times n. And if I plot the one-sided power spectral density, what I'll get is the following. So let's say this is my bin k. I'll have 0 to n by 2. At the mth bin, I'll have an impulse corresponding to the input, fundamental frequency, right? And since I have third harmonic, I'll also have an impulse at say 3 times m. Similarly, for the fifth harmonic, I'll have at 5m, right? And all the other bins will be filled with quantization noise. Okay. And in practice, we'll not only have the quantization noise. So this portion, this flat portion, will be both due to the quantization noise and the circuit noise. Okay. So there are two parameters, that is two metrics we use to characterize the ADC. So one is called the signal to noise ratio. That is SNR. And we compute it as the following. We take the ratio of the signal power to only the noise power. That is, what we do is, while computing the noise power, we take only the strength of these bins alone. That is, we ignore the harmonics. So we don't consider the strength of these harmonics in computing the noise power. Okay, so this only captures the effect of the noise. Okay, the other measure to characterize the linearity of the ADC is this, that is signal to noise and distortion ratio. So abbreviated as SNDR or sometimes as SINAD. Okay, signal to noise and distortion ratio. And this is computed as the ratio of the signal power to the sum of noise and the distortion components. Right, so to compute this SNDR, this gives the signal power, right? And the sum of all the other bins, okay, that gives this. That is the sum of the noise as well as the distortion products. Okay. And if you remember, we also defined the effective number of bits. So in an ideal case, we computed it as follows: SQNR minus 1.76 by 6 bits, right? But of course, now we see that in practice, we not only have the quantization noise, we also have the circuit noise and the distortion products, right? The harmonics. So instead of using SQNR, what we use is this SNDR. Okay, so this is how we compute the effective number of bits in practice. Okay. So let's say I give the same input as this, that is cos 2 pi times 201 by 8.92n, this sinusoid, to an ADC which has both third and fifth harmonic distortions. That is, it has both third and fifth order non-linearity. So let's see what the spectrum is. Okay, so as we expect, along with the signal bin, that is the bin 201, we also see two impulses corresponding to the third harmonic and the fifth harmonic, right? So this is 3 times 201, that is 603, and this is 5 times 201, that is 1005, right? So what is the SNDR for this? Well, I suggest you please pause the video and try to quickly estimate what is the SNDR for this from this spectrum. Okay. Well, so how do you do? Well, before we saw that for the same ADC, if we do not include these distortion, that is this harmonic strength, the sum of this noise power was such that the ratio of the signal to this noise power was around 62 dB. Right? And that's what we saw earlier. So which means the signal power here is around minus 3.72 dB. So which means the sum of these bins, sum of all the noise bins is roughly, say, minus 65 dB. Okay. But what is the strength of the third harmonic? That is minus 43 dB, right? So that's around 100 times higher than the sum of this, the total noise power. So which means if you add the strength of the third and fifth harmonics along with the noise power, it will finally be dominated by this guy, right? Because this is 100 times higher than this, right? So what will be your final SNDR? Well, SNDR will roughly be the signal power, that is minus 3.72 dB, minus the strength of this third harmonic, that is minus 43.6 dB, right? So that's roughly 40 dB. Okay. And from this, you can back calculate what is the effective number of bits, and that's probably around 6.2 dB or something, right? Okay. And if I keep increasing the input frequency, that is, if I change the bin position of the fundamental to say this frequency, now the fundamental is at 801. So what will happen? The third harmonic will be at 3 times that frequency, that is 2403, and the fifth harmonic will be located here. Okay. So now if I keep increasing, that is, if I keep increasing the input frequency further, so what will happen? All these impulses will shift, right? And it can so happen easily that this fifth harmonic will lie outside this, right? So this is from 0 to 4096. Okay. So this can easily go outside 4096, and once that happens, what will happen? It will alias back, right? So let's see an example. So here I've taken the input bin to be 903, right? So what is the third harmonic? That is 3 times 903. That is what? 2709, and that's what we get, right? And the fifth harmonic is what? Ideally, it should have been at 5 times 9903. That is 4515, right? And this is obviously greater than 4096. Okay. So what will happen? It will alias back to n minus 4515. That is, n is 8192 here, minus 4515. That is this value. Okay. So the other way to understand this is, so the signal is at bin 903, right? So this corresponds to a discrete time frequency of 2 pi times 903 by 8192, right? So which means the fifth harmonic is at 5 times this frequency. Okay. And that is 2 pi times 4515 by 8192. Right? This is obviously greater than pi. Right? So what will happen? This will alias back to 2 pi minus this. And that will be this frequency. Okay. And the other thing to note is that in all these plots, say even in the earlier plot and in the other plots as well, the strength of the third harmonic is lesser than the fundamental, right? And the fifth harmonic is further lower, right? Well, this is expected because in the first place, we were trying to design an ADC which is highly linear, right? So which means we expect that the fundamental strength of this fundamental frequency will be much higher, and the strength of the higher harmonics will be lower and lower. Okay. Now, in this case, the fifth harmonic aliased back and came back to this point, right? But now if I keep increasing this input frequency further, so it can easily happen that the third harmonic might not alias back, that might still be within this limit of 4096. But what can happen is the fifth harmonic can alias back and fall to a frequency that is lower than the third harmonic. Okay. So this shows such an example where the fundamental, that is the frequency of the input sinusoid, is 1051 by 8192 times 2 pi, which means the input occupies this bin 1051, right? The third harmonic is 1051 times 3, right? That is this 3153. Okay. And the fifth harmonic is 5 times 1051. Okay. And that is probably 5255 or something. So this will alias back to this bin, and that is this. Okay. So if you don't know this, you might think that this is slightly weird because, you know, we expect from our intuition that the strengths of higher frequencies, I mean, the strength of higher harmonics should be lower and lower. So we expect that we should get something like this, right? The strength should keep reducing. But here you see that this bin, that is this frequency, has a lower strength, and the higher frequency here seems to have a higher strength. Okay, and this is happening because our higher frequency component, that is the fifth harmonic, has aliased back and fallen back to this frequency. Okay. So again, in all these cases, remember that the SNDR of the ADC is around 40 dB, right? So I've taken the same ADC only that we saw earlier, that is here, okay? And I just changed the input frequency, right? So in all these cases, the SNDR is still 40 dB. Okay. Now let us say I take the same ADC which has SNDR of 40 dB, okay? Right? And I feed an input sinusoid such that after sampling, it has this form, that is cos 2 pi times 1000 by 3000. Yeah. Okay. And say I take 3000 samples of this, that is 3000 samples of the ADC output, right? And find the power spectral density using a 3000 point DFT. Okay. So let's see what we get. This is the plot we get. Okay. So all these bins here, they are at around minus 250 dB or so. That is essentially 0, right? That's just MATLAB way of representing 0. This is log 0. This ideally should be infinity. Sorry, minus infinity. But this is like minus 250 dB. That's 0. Okay. And we clearly see that we have only 2 bins, right? One is at DC and one is at 1000. So this 1000 is something we expect, right? Because the input we chose was of this form, right? 1000 by 3000 times 2 pi. So if I take a 3000 point DFT, right? So this should lie on the 1000th bin. Again, notice that this is varying from k equal to 0 to k equal to 1500. This is the one-sided spectrum. Okay. So here we have this corresponding to the input, and we also have a DC component. Okay. Well, in practice, this DC component might come due to some offsets in the circuit. Okay, so we might think that, well, the ADC has no quantization noise and it has no distortion products, that is no harmonics. So you might think that you have designed an excellent ADC, right? But obviously it is not the case, right? It is the same ADC for which we saw the SNDR was 40 dB. So what do you think is happening? Again, I suggest you please pause the video and try to find it. Okay. Well, if you found it, it's great. Else, let's try to find it, why that happened. Okay, so this was the input frequency this was the input signal that we gave, right? And how does this simplify to? This is cos 2 pi times n by 3. Okay, so which means this has only a period of 3 samples. That is, even if I take 3000 samples, it has only 3 unique values, right? So maybe it just looks something like this. Okay, something, I don't know. So which means even the quantization noise is going to be periodic, right? So that will also be some periodic signal like this, something, right? And when you take the discrete Fourier transform, it assumes that we have the same chunk of signal. That is from, let's say I took 0 to, this is 2999, 3000 samples. So the same thing will get repeated on either sides. Okay, so overall, it assumes that we are dealing with a signal that is periodic with a period of only 3 samples. Right? And we know that if a signal is periodic with 3 samples, it has only 3 distinct frequencies, right? What are they? 0, 2 pi by 3, and 2 times 2 pi by 3, right? Because, well, if you take the 3 times 2 pi by 3, it is simply 2 pi, right? And that's same as 0, right? Similarly, all other higher harmonics will simply be one of these frequencies. Okay. And even in these 3, we have 0, 2 pi by 3. 4 pi by 3 is greater than pi, right? So how it will look? So it will be same as 2 pi minus 2 pi by 3, isn't it? So which means even this frequency, 4 pi by 3, when you look at the one-sided spectrum, it will fall on the same frequency, 2 pi by 3. Okay, so essentially we will have only these 2 frequencies showing up in the spectrum. Okay, and this corresponds to our 0th bin. And this corresponds to 2 pi is 3000, right? So 3000 by 3, that is 1000. And that's what we saw, right? For the same reason, even if the signal is getting distorted, that is harmonics of the signal, they will also lie on k times 2 pi by 3, right? These are the harmonics of the signal, right? So the third harmonic will be 3 times 2 pi by 3. That is same as 2 pi, right? And the fifth harmonic is 5 times 2 pi by 3. And you can easily find that this will lie on 2 pi by 3, right? That will fall back to 2 pi by 3. And this 2 pi is same as 0. Okay. So finally, even though you have quantization noise and the harmonics of the signal, all of them will just alias back and lie to these two bins. Okay. And we'll wrongly think that the spectrum the signal has no harmonics and there is no quantization noise, which is obviously not the case. Okay. So why this is happening? Because we chose the frequency such that m by n, they are not coprime, right? So here, what did we choose? We chose the frequency to be of this form, 1000 by 3000 times 2 pi, right? And these two are not coprime. Okay. So this is one more reason as to why you should choose your input frequency of this form.